Hello, my name is Alisha Bhatia,
I'm Greeshma Avaradi.
And I'm Ben Sherwin.
and we are Team 1051 from the University of Florida. Our coach is Dr. Tracy Stepien, and today we'll be exploring our approach to problem B, throw the bike or throw the race. Today, we'll take you through our goals, the creation of our model, an analytical solution, and finally, we'll discuss what this model tells us. Bike throw is utilized in the final moments of a race, just after a biker sprints. Bicyclists immediately stop pedaling as they shift their weight back and extend their arms to throw or push the bike forward, allowing them to gain additional distance. Next slide. Here we can see the technique used by Winder to defeat her opponent just this year. Next slide. Next, let's go through our preliminary model.
We started with the most basic model possible to try and better understand the situation of the problem. This involved a bicycle with just the force of quadratic air resistance acting on it. We chose specifically quadratic air resistance since we thought it would be more impactful than the force of friction from the road, operating under the assumption that the bicycle tires would be much more well lubricated and have high air pressure. Using Newton's second law, we were able to write a differential equation involving quadratic air resistance and solved it by a separation of variables with initial conditions implemented. We used a very similar strategy in our actual model, so this methodology is very important for our model with the bike throw. We also have a few graphs next, and the left graph represents velocity versus time, and the right graph represents position versus time of this simple model. Next slide. For our actual model, we made several assumptions once we were able to understand the situation better with the preliminary model. One of the biggest assumptions that we were able to make was making the force constant instead of implementing a form of time dependence. Since we're looking at such a small interval of time, this is a pretty valid assumption. And the reason we did this is because time varying forces are much harder to solve with differential equations to solve analytically. So we restricted ourselves to more analytical solutions and tried some numerical techniques, but overall we went with analytical solution. And we also could have used more advanced mathematical techniques to improve the accuracy of our differential equation. So we also included the bike throw and the weight shift occur at the same time to simplify this kind of motion. Next slide.
We also assumed that the shifting center of mass was negligible, that the bicycle was completely upright so that no torques could cause rotational forces, that the magnitude of the force of friction is much less than that of the force of the bike throw, so that we can restrict our solution to real numbers, that the bicyclist is riding on an asphalt road, and that the shape of the bicyclist is roughly hemispherical for the purposes of air resistance. Next slide. Here are some of the ranges and units of our parameters, which are first mu k, or the coefficient of kinetic friction, F sub bt, the force of the bike throw, V naught is the initial velocity when sprinting, M is the bike rider system mass, and T naught is the moment at which the bike is thrown. C is the coefficient of air resistance, which we calculated using the formula C equals 1/2 rho dA and found the values for those variables from literature. Now let's talk about finding an analytical solution.
We employ the use of the same techniques we used in the preliminary model, which involves using Newton's second law and a free body diagram, which is pictured below. And we can write a differential equation for the motion in both the x direction and the y direction. However, the y direction forces are very balanced, so the normal force is equal in magnitude to the force of gravity, which is very important in determining the force of friction. On the right-hand side of our differential equation, you can see that we have the quadratic air resistance as well as two constants, which are the force due to friction and the force of the bike throw. Again, we implemented separation of variables to solve this differential equation, but in order to get an integrable expression, we had to redefine our constants so that the form of the integral would be solvable. In this process, we had to assume that beta, which we label as the force of the bike throw, was larger than alpha, which is the force due to friction, so that gamma and delta would both be real numbers, so that integral is well defined. Overall, we are able to get a closed form expression of t in terms of v, which is in the right-hand corner, but we are unable to isolate v in terms of t due to the complexity of this expression. Next slide. Also, we were able to produce a plot of the velocity versus time in Python. And we can see that there's a noticeable spike in the velocity when the bike throw is applied, which is basically what we'd expect to see given our parameters of the model. This graph helps us understand the behavior of our solution and also helps us look at some key facts about the timing of the bike throw. Next slide.
Here we've incorporated another bicyclist to measure the effectiveness of the bike throw. We have bicyclist A and B, who both have a sprint in the beginning, but then A does a bike throw while B maintains the sprint until the end of the race. We see that A's velocity sharply increases faster than B's, and the velocities diverge around the 12.5 second mark. This graph helps us to visualize how the bike throw can be vital in giving an extra boost and comes in handy when determining timing. Here we go over the implications. When should a rider stop pedaling and shift her weight? We divide the graph into different areas. Little a represents the area under curve A and above curve B between times T0 and TF prime. Little b is the area under curve B between times TF prime and TF. We know that A equals B since the displacement of biker A between 0 seconds and TF prime seconds is equal to the displacement of biker B between 0 seconds and TF seconds. Both displacements represent the total distance of the race. We need to find T initial. That's our goal. Here we see the consequences of throwing too early versus too late. In the left, we see that if the rider shifts too early, then T0 is shifted to the left, and that the bicyclist reaches a peak velocity too early, and their velocity declines quickly as friction overpowers the drifting bicycle. Then A is less than B. On the right, we see that if the rider shifts too late, then they risk being behind and unable to complete the entire bike throw to their full advantage. We see that area A is less than area B again. In both cases, A is less than B, which means that the blue bicyclist will be unable to finish the distance before the orange bicyclist, bicyclist B, who does not do a bike throw. This will render the bike throw useless. So when should the rider shift? For the bike throw to be effective, we have to make sure that T0 is not too early nor too late. And A has to apply the bike throw such that A's finishing time is before B's finishing time. Here we assume that bicyclist A does not stop, but rather continues to drift, but not pedal after the finish line. We have to place T0 such that A plus C is greater than B. Here, C is the distance that A travels after the finish line. Therefore, we see that A plus C must be greater than B. And since A must equal B, then C is at least is greater than 0. If C is less than 0, then we know that the bike throw was applied either too early or too late. If C is equal to 0, the race is a draw. And this means that A and B cross the finish line at the same time, which means that the bike throw was ineffective. With the current values we've used for our parameter ranges, the graph shows that the bicyclist should stop pedaling and shift at approximately 12 seconds. Now, what's the time interval that the bicyclist must exploit for the bike throw to be effective? Our time interval is determined by TF prime minus T0, and the bicyclist A must ride through the entire peak of the velocity increase so that they can take the fullest advantage of the bike throw and continue until A is equal to B. Now, if A is less than B, that means that A either started the bike throw too early or they didn't complete the maneuver, which means that B crosses before A. This causes A's finishing time to be greater than B's finishing time. With our current parameter ranges, we see that the time interval of the entire bike throw is approximately 5 seconds. Now, what's the maximum amount of time that can be made up? We denote this time as TF minus TF prime, and this represents how much time bicyclist A saves in order to finish the bike race with the bike throw compared to the bicyclist who does not apply a bike throw. First, we see that the difference in time is at its minimum when C is equal to 0. Therefore, to maximize our difference in time, we have to maximize C while keeping A equal to B. With our current parameter values, we see that bicyclist A beats bicyclist B by approximately 3 seconds. So the maximum time that A makes up by using a bike throw is 3 seconds. This is a higher value than we expected, but this is likely due to our assumption that the bike throw is a constant force.
We can also look at the hand position, which we didn't include in our original differential equation, so we decided to answer this question separately. We decided simply to consider the effect of the hand position instead of incorporating it by itself into the model. So namely, we're looking at the torque that arises from shifting hand positions. Mathematically, we can look at the torque as the cross product between the distance from the pivot and the force applied. This implies that applying the force at a right angle would cause the greatest torque and hence the most instability, which is what we want to avoid. So we can conclude that the best hand position would be to keep your hands close together and not move them extensively. Next slide. Also, we certainly can make improvements on our model. Given more time, we definitely would have tried implementing a time-dependent force instead of leaving it as a constant. So mathematically, this would involve the use of the Heaviside unit step function or the impulse response function. This was probably one of the largest sources of error in our model, so it would definitely improve it if we implemented it accurately. But the reason we didn't use this is because it would have been difficult to solve analytically. So that's why we avoided this. Also, we could make significant improvements in our model by using more computational numerical techniques. And we were able to use Python a little bit for some of the model, but I think that for using sensitivity analysis or other methods, it certainly would be helpful to use more Python to add more mathematical justification to our answers for our questions. Also, that sensitivity analysis I mentioned would have definitely been helpful in testing out how our model behaves and what affects it the most. Next slide.
This is the end of our presentation. Thank you for listening.